Since its founding days in the 1960s, researchers at SLAC National Accelerator Laboratory have been generating beams of electrons to study some of nature's best-kept secrets. In the past, scientists used these beams for powerful particle collisions that revealed fundamental building blocks of matter. Today, SLAC uses its electron accelerators mostly for the generation of X-rays. These are emitted as the flight path of electrons is bent by magnets at the Stanford Synchrotron Radiation Light Source, SSRL, and at the X-ray Laser Linac Coherent Light Source, LCLS, one of the most powerful X-ray sources on Earth. Recently, SLAC researchers have begun to explore another way of using electrons to probe the inside of materials, with a method they call ultrafast electron diffraction. Electrons are generally viewed as particles, yet they also behave like waves, similar to waves of light. The higher the energy of the electron, the shorter its wavelength becomes. If the wavelength is short enough, the electron wave can collect information about the atomic structure of the object that it passes through, just like X-ray waves reveal the inside of materials. Using this property of electrons, researchers can build a new setup for ultrafast electron diffraction. It all starts with the production of a high-quality beam of very energetic electrons, based on a technology developed by SLAC for LCLS. This is done inside an electron gun, where a laser pulse heats a piece of metal known as a photocathode and evaporates electrons from the metal. This incredibly short bunch of electrons is then accelerated by a radio frequency field toward the exit of the gun, where a magnet focuses consecutive bunches into a narrow beam of electrons, traveling at 99.3% of the speed of light. Researchers then shine this beam through a sample. The incoming electron waves scatter off the sample's atomic nuclei and electrons, producing scattered waves that combine to form a characteristic pattern on a detector. This process, called electron diffraction, allows scientists to reconstruct the atomic arrangement in the sample. Because the electron beam consists of a train of very short, widely spaced bunches, researchers can also see ultrafast changes in a material structure that occur in less than a trillionth of a second, for instance in response to laser light. This technique is similar to X-ray diffraction, where scientists shine X-rays through materials. However, electron and X-ray waves are sensitive to different things, and therefore complement each other. X-rays scatter off electrons only and cannot see atomic nuclei directly. Electrons, on the other hand, are sensitive to both electrons and nuclei, providing additional information. One example where X-ray studies at LCLS and ultrafast electron diffraction experiments go hand in hand is magnetic materials. Magnetism arises from a property of electrons known as the electron spin, which is often compared to a ball spinning on its own axis. These spins float around the material's nuclear core structure like an electron sea. But how does the interplay between the electron sea and the nuclei impact the magnetism of the entire material? Researchers want to find answers because a better understanding could help them build new or better magnetic materials that could be relevant to data storage devices and other applications. Beyond materials science, researchers also hope to use ultrafast electron diffraction to record molecular movies and observe atoms and molecules as they move during chemical reactions. But researchers don't want to stop there. They want to take the technique to the next level. Electron diffraction produces a rather abstract diffraction pattern, so researchers have to reconstruct how a material looks on the inside. Electrons can also be used to take images of samples directly. By inserting magnetic lenses in front of and behind the sample, the electron diffraction setup is turned into an electron microscope, similar to its optical counterpart. However, since electrons have a much shorter wavelength than visible light, an electron microscope can see much finer details close to the atomic level, such as domains in magnetic materials. The fastest existing electron microscopes can take snapshots of processes as fast as 10 billionths of a second. The SLAC researchers hope to improve this time resolution up to 1,000-fold for more snapshots of the same process in a given time. This would open up new possibilities for ultrafast science.